mostly interacts with arginines and lysines on the protein. Some extent with hydrophobic groups, because there's a lot of hydrophobic characters to masculinity groups that hydrophobic groups in the protein interact with it. Proteins will usually unfold because it's in this acidic solution. So then you have to satisfy the hydrophobic complexes. But that will basically stabilize the negative charge here and give you. And so here are some examples of how you might do that. So this is using 1 centimeter coupling cuvettes. Here's 5 of them. Here's maybe a slightly more rigorous experiment to get a greater range. For the brown stuff, it's no protein or low protein concentration. Increase the protein concentration. It increases absorbance over time or over concentration. You need to do a plot like this. The protein concentration, in this case, it's known versus the absorbance at 595. And you get basically a standard curve. Then you can do exactly what I look here. Here's the different structures in a set of these experiments. So this is subtracting the starting structure. That's the spectra, and you go up at 595, put down. You change it. Now you can look at this experiment. The field kind of mimics that experiment. I don't think it's a great experiment because we did 6 samples, but only 2 of them are really useful. This one right here is basically baseline. These 2 are in the middle. The last 3 were all saturated. They were up at the top of the curve. They all basically had the same color. It wasn't very wisely done. But you can, again, use the standard curve. People often will do this in microtiter plates. So here you can get 8 concentrations in a row in the 6 plates, which is a nice, easy way to do it. The amazing, did you get any horrible with it? No, small. But still a microtiter. Keep in mind when you do a microtiter plate, the pathway you use depends upon the volume. You put more volume in that well, you create a longer pathway. Normally you run your standards on the same plate, so you don't have to worry about it. The standard should have exactly the same volume. If the standards have a different volume, they have a different pathway, they have a different. But then the other thing I want to point out here, that's a problem with the graph, is that these are all proteins of known concentration. So there's BSA here, and then there's an IgG molecule. If you notice, the IgG is hardly giving you a signal at all, versus the BSA, they gives you a very nice signal. You can solubilize them in detergent, I think you get these 2 signals with the dash. But what I want to point out is that the 2 proteins differ quite a bit in the absorbance signal they're getting. Why might that be the case? Oh, yes. How much arginine and lysine in effect? Because the Bratcher reagent mostly binds to acidity, or the basics of the protein. So if you have more arginine and lysine in the protein, you'll detect it more efficiently. And it'll last if you want. So if this becomes your standard curve, these 2, you can put in your unknown protein and plot it out this curve. And if your unknown protein, at 0.5 absorbance units, you would get 0.2 mg per ml if you use BSA as your standard, but you would get 0.8 mg per ml if you use IgG. So not an ideal world. But at the same time, the assay does work. What you can do is actually do that assay, and then maybe one time do this kind of experiment, find a sample, and this may take a lot of material, but you do it once, you get a real concentration based on the curves. And then you say, okay, I'm going to take a look at this sample and put it into the Bradford assay. Maybe the Bradford assay is going to come out and tell you, it's 1.5 mg per ml. And this one here translates to 2.2 mg per ml, and so you just have another correction factor. When I do this in the Bradford versus, say, bovine serum albumin as a standard, I get this number. I'll multiply that by 50% higher, and I get 30. Again, in your head, you could do this correction factor. So if you did this with IgG as a standard, you would get it. But so the Bradford assay is known for having basically protein removal, variation from protein. This is actually a table that comes out of just an instruction manual for the assay, just pointing out for a whole bunch of proteins. Even IgG from rabbit versus sheep, versus human, it can differ almost twofold. So different proteins are detected at different efficiencies. But sometimes it's really convenient to use because it's fairly sensitive and you can use it in some microplates. It takes less material than maybe doing it. I also want to point out just this operation, any assay you ever do has chemicals that are compatible and chemicals that are not compatible. So this is from Bradford's original paper, and he basically looked at it in the presence of molar concentrations of salt, sucrose, ethanol, etc., and saw the absorbance change he saw with that, and then he said how many micrograms of ESA does that correspond to. And most things here are pretty low, except acetone. You don't use acetone a lot, so it's not that big deal. But then suddenly Triton and STS, which are two fairly common detergents, have huge effects. So detergents end up really being bad news for the Bradford assay. The detergents will interact with all these hydrophobic groups and drive the color change by interacting. So the Bradford assay is not a great assay if you have a lot of detergents. And then here's a whole other list. I don't expect you to memorize this. I want you to realize this list exists. If you do this assay ever, or any assay you ever do in a biological setting, there is a manual that comes with it, and it will often have a table like this that tells you what you can and cannot do with that. Okay, so we have one more assay I'm going to talk about briefly, which is this thing called the minute. It's a mouthful. So it's called the BCA assay for protein quantitation. And it was actually the predecessor to this was called the Lowry assay, which is based on something new, rather than some funky assay. But basically what this one is that you can reduce copper 2 plus to copper plus with a peptide bond. So copper combined to the peptide bond, interact with the peptide bond. If you heat that solution up a little bit, you reduce copper 2 to copper. And it changes color in the process. And it goes from being a green copper complex to being a purple complex. When it's been done in the presence of BCA. So this is the BCA molecule. You throw copper on that, these nitrogens with the chelate, and two BCAs will come together and chelate and copper into a complex. And the copper here is chelating these nitrogens. This is nice purple. So it really is a two-step assay, where first you convert copper 2 plus to copper plus, based on peptide concentration. And that peptide backbone, so it's not side chain sensitive. It doesn't really care what the switch is. Proline is maybe a little less efficient because backbone is constrained, but there's so few proteins. So you do that first, and then you mix it with BCA, or maybe actually it's all done in the presence of BCA, but then the color evolves. So here is ESA, again, just go on serum albumin versus the OD at 37 degrees. You can incubate it for 30, 60, or 80 minutes. You get slightly different ratios, but basically it's close to a linear difference. This is the absorbance versus how much protein was in there. Not surprisingly, you let the reaction go longer to form more copper plus, and you get accuracy. At 37 degrees, maybe not so bad. You could do the same thing at 60. Notice these are not close to 2 absorbance units. This is now 1.2 absorbance to 1.4 absorbance. So 60 degrees, it goes even better. Your sample also evaporates more at 60 degrees. You have to make sure you don't concentrate your sample by evaporating it all. But that is basically BCA assay. And this is what the spectrum looks like. So this is just the increasing amounts of the copper BCA complex over time. So you can just tell that increases. It goes on. You can look at a couple of different proteins here, and there is some variation in this assay too. If you notice, averaging all of these proteins, the average is 1.02 with like a 15% error. If you go back to this Bradford assay, the average is 0.7 with 38% variation. So the Bradford assays is not very good versus the BCAA assay, which is much more reliable on the same pool of kind of representative proteins. And again, there's a chemical compatibility list. One thing I want to point out there is that this assay is not compatible with producing agents. That's the problem with it. We often use benzocath ethanol or EPT, which is trisulfide proteins, and that will immediately reduce the copper for you, independent of the phenotype. Again, this is present at micromolar to millimolar concentrations, so immediately your solutions are. So if you have reducing agents, can't do this BCA assay. There is a reducing agent compatible assay that does a pre-treatment step to oxidize reducing agents. So you can quantitate. So those are kind of three assays: straight absorbance, the Bradford BCA, three assays for protein quantitation that basically are using absorbance spectrometry. Any questions on that? Okay. So the last 5 minutes, I'll do a little primer to light polarization, which we'll start dealing with as we go into the dichroism spectroscopy on Friday, and also fluorescence. So if we go back to the very first slide that I drew, I kind of drew this wave and pointed out that it has this electric component, and then it also has a magnetic field component that's perpendicular. So if you were to look at this light wave coming out at you, it's heading straight at you. The electric component is going to be going up and down on any one photon. But the photon zipping along next to it may have its electric component or this, or that, or this. So we have this whole collection, which is kind of cartooned on here. And normally when we have what a non-polarized light, there's no order to that electric component, or the magnetic one that's 90 degrees to it, but we don't care about it. So the electric component is basically red. Well, it turns out there are times when it would be really useful to have that not void. So we can not randomly orient, so you can get one position. So we can do that via a polarizer. In effect, the polarizer is see if this no, of course. Oh yeah, actually that will work. So there's a polarizer. Sorry, there's a polarizer. So that's light that's now being polarized. And in fact, we're selecting light that has a certain orientation of electric field. If I take that away, you see a lot of light. You can basically cut out some of the light now that has that light. Only insert one orientation. And here I have a second polarizer. That looks very much like the first polarizer. But what happens if I put these two on top of each other? That's. Now, in fact, I get no one. If I rotate one of them relative to the other, I'll get a little one. So these are both selecting light. If I set them so that they both select light going this way, whatever gets through the first one can get light through the second. But if I rotate that second one 90 degrees, and whatever gets through the first one is the stuff that's impossible to get through the second. Because they're both selecting, this is plain polarized light. And therefore you see nothing. If I go somewhere in between, I kind of get some intermediate intensities, and then I line up perfectly. And so basically, the polarization will select out this subset of light. You get a wedge of photons that have their electric moments lined up. And that's kind of what's cartooned on here. So you can imagine You have a circle where these are random. You could perfectly select everything going that direction. Or you could do a reasonable job of selecting, so now it's narrower in the xy or x direction than it is. Oh, true, good point. The polarizer is sitting there, my finger can't Got better? Yeah. So you start with this. If you do really polarized, you can select a very small wedge of the photons. You get little light intensity. You're throwing away 95%, 99% of your photons, but you're selecting the ones that are perfectly. Or you can select somewhere between that as good, so you have some in that dimension, but most of them. You can define this degree of polarization as just whatever is parallel to what you want to see minus perpendicular divided by the sum. So if you're highly polarized, this perpendicular is 0 in effect. Here's everything is parallel. And then if these two are equal to each other, then that whole top term becomes 0. Because parallel and perpendicular are basically the same. So either you get it all parallel or you get it. I think I will stop there and bring this up.